You're looking at the most dangerous stretch of ocean on Earth. Winds circle the planet here without hitting land. Storms stack on top of each other. Waves can reach 50 feet high. This is the Drake Passage. And in this video, I'll explain exactly what makes it so extreme, how ships survive it, and why people keep going back. The Drake Passage is a body of water located between the southern tip of South America and the northern edge of the Antarctic Peninsula. It connects the Atlantic Ocean with the Pacific Ocean and forms part of the Southern Ocean that circles Antarctica. At its narrowest point, it is roughly 600 miles wide, and at its deepest, it reaches nearly 6,000 meters, about 4 miles. On a map, it doesn't look particularly dramatic. In reality, it is one of the most energetic, storm-driven, and complex regions of ocean anywhere on Earth. It has some of the highest average wind speeds on the planet, some of the largest average wave heights, and some of the most extreme weather variability. Sailors have feared it for centuries. Scientists study it because it plays a critical role in Earth's climate, and modern travelers cross it as part of voyages to Antarctica. The Drake Passage exists because South America and Antarctica are not connected. They almost are, but not quite. South America extends southward into a narrow tip at Cape Horn. Antarctica extends northward into a narrow peninsula. Between them is a gap, and that gap is the Drake Passage. This gap is important because it allows ocean water to flow freely all the way around Antarctica without hitting land. That flow is called the Antarctic Circumpolar Current, the largest ocean current on Earth. Unlike the Gulf Stream mentioned in previous videos, which is constrained by continents, this current flows endlessly around the globe, and the Drake Passage is the narrowest choke point in that system. That means a huge volume of moving water is being forced through a relatively narrow space. That alone increases speed, turbulence, and wave formation. The Drake Passage sits between 40 and 60 degrees south latitude. These latitudes are famous among sailors. They're called the Roaring 40s, the Furious 50s, and the Screaming 60s. These zones are dominated by strong westerly winds that circle the planet. In the northern hemisphere, winds are interrupted by continents, mountains, forests, and cities. In the southern hemisphere, at these latitudes, there's almost no land at all. That means winds can travel thousands of miles without even slowing down. They gain energy continuously. By the time they reach the Drake Passage, they are fast, stable, and persistent. These winds push energy into the ocean surface, creating large, powerful waves. Waves in the Drake Passage commonly reach 25 to 40 feet. In extreme storms, they can exceed about 50 feet. For comparison, typical Atlantic waves are often around 2 to 4 feet. The Drake Passage carries an enormous volume of water eastward. The Antarctic Circumpolar Current transports more water than any other ocean current on Earth, more than 100 times the flow of all the world's rivers combined. When this current passes through the Drake Passage, it speeds up. This increased flow interacts with underwater terrain. There are submerged mountain ranges beneath the Drake Passage. As fast-moving water flows over and around these features, it creates turbulence and internal waves within the ocean itself. These internal waves mix deep, cold water upward with warmer surface water downward. This mixing plays a key role in global heat distribution and carbon storage. In other words, the Drake Passage is not just stormy. It is one of the main places where the ocean's deep and surface layers interact. That makes it critical for Earth's climate system. Before the Panama Canal opened in 1914, ships traveling between Europe and the Pacific coasts of the Americas had two realistic options. They could unload their cargo on one side of the continent, transport it across land, and reload it onto another ship. Or they could sail all the way around South America. Moving cargo across land sounds simple, but in practice, it meant transferring tons of goods thousands of miles using railways, wagons, rivers, and ports that were often incomplete, slow, or unreliable. Cargo had to be unloaded by hand, stored in warehouses, inspected, moved again, and then reloaded onto a second ship. Every transfer increased cost. It increased the risk of damage, theft, and delay. A single shipment might be handled dozens of times before reaching its destination. And in the 19th century, there was no standardized containers. Every crate, barrel, and bale was moved individually. The alternative was to keep everything on one ship and sail around the bottom of the continent. That meant adding more than 8,000 miles to the journey. It was weeks or months longer at sea. And it meant passing through the most dangerous waters on the planet, around Cape Horn and through the Drake Passage. But for many companies, that risk was still cheaper and more predictable than unloading, transporting, and reloading entire cargoes across an undeveloped continent. So ships kept going south, around Cape Horn, not because it was safe, but because it was simpler. Cape Horn became infamous. Storms, waves, ice, poor navigation tools, and wooden ships made the journey extremely dangerous. Thousands of sailors died there. Entire fleets were lost. The Drake Passage became associated with wrecks, disappearances, and extreme hardship. It gained a reputation not just as dangerous, but as unpredictable. Even experienced captains could be caught by sudden storms. That reputation persists to this day. Today, ships crossing the Drake Passage rely heavily on modern weather forecasting. Meteorological models allow captains to track storm systems days in advance. They can time crossings to avoid the worst conditions. They can adjust speed to pass behind or ahead of low-pressure systems. They can change headings to reduce how waves strike the ship. Captains do not simply aim straight across. They often take longer, angled routes to improve comfort and safety. Crossings are planned many days in advance, and forecasts are checked multiple times per day. If conditions look severe, ships will simply wait, but some choose to brave the chaos. Despite modern ship design, forecasting, and navigation systems, the Drake Passage can still deliver conditions that exceed what even today's vessels are built to anticipate. One of the most serious recent incidents occurred in late 2022, when the cruise ship Viking Polaris was crossing the Drake Passage. A breaking wave, effectively a rogue wave generated by the combined action of high winds, currents, and sea state, struck the ship's side at night as it was returning from Antarctica. The impact was powerful enough to shatter 7 stateroom windows, causing significant interior damage and flooding to parts of the vessel. In that incident, 1 passenger was killed and 8 others were injured. The investigation later found that while the ship was operating within its designed wave conditions, the force of the breaking wave exceeded what the windows were engineered to resist. This event is a sobering reminder that even the most modern expedition ships with reinforced hulls, stabilizers, and advanced forecasting cannot eliminate all risk within the Drake Passage. It also shows why crews take storms seriously, adjusting course, slowing speed, and securing everything on board, and why passengers are advised to remain in the cabins during the worst of conditions. Yet importantly, despite this tragedy, the vessel did not sink. The ship remained seaworthy, the crew maintained control, and thankfully, most people were able to reach safety thanks to the redundant systems and emergency protocols. This incident illustrates the gap between design limits and nature's extremes, and underscores why respect for the Drake Passage lies not in fear of catastrophe, but in understanding of the sheer scale of forces at play. Modern polar vessels are built specifically for rough seas. They have stabilizers to reduce rolling, strong, reinforced hulls, specialized bow shapes to cut through waves more smoothly, and heavy ballast to improve stability. Some ships use inverted bows that ride through the waves instead of slamming over them. Passenger areas are designed with low centers of gravity and secure furnishings, so that in heavy seas, objects don't become airborne hazards. Windows are often large so passengers can see the horizon, which reduces seasickness. These ships are extremely safe. They're designed not just to survive storms, but to operate comfortably in them. Crossing the Drake Passage usually takes between 36 and 48 hours. Sometimes it's calm, and sometimes it's rough. When it's rough, the ship may roll significantly. Walking becomes difficult, items slide or fall, and sleeping can be challenging. People react differently. Some feel sick, some feel fine. Mostly though, people take medicine to counteract the effects. Despite everything, people continue to cross the Drake Passage. Scientists cross it to study climate, ocean currents, and ecosystems. Tourists cross it to reach Antarctica, one of the most remote and unique places on Earth. For many, the crossing is part of the appeal. It makes Antarctica feel earned. It makes the journey feel meaningful, and it creates a psychological separation between the familiar world and a completely different one. The Drake Passage is feared because it is a point where multiple large systems overlap. Atmospheric circulation, ocean circulation, and the open geography all intersect here without interruption. Each system is stable on its own. Together, they produce a level of energy and motion that is more intense than any location on Earth. Ships that cross the passage are built and operated with that reality in mind. Their design, routing, and timing are all shaped around managing it. What makes the Drake Passage demanding is not that it behaves strangely. It behaves exactly as expected. It follows the same rules as the rest of the planet, just without anything in place to moderate them. That is why it remains difficult, not because it is exceptional in nature, but because it is ordinary physics operating at full scale. If you want to keep exploring real stories that are hard to believe, you can subscribe below. More of them are on the way, and thank you for watching.